Okay, so by way of summary, we said yesterday that the derivative of sine was what? What was the derivative of sine? Cosine x, right? Okay, so that was just something we saw graphically, and we didn't really try to prove it. Did anyone take the time to prove that last night? Okay. So you've still never done a difference quotient with a trig function. Okay? Might want to do it. Okay, so sine x, the derivative came out to be cosine x. And then we talked about cosine x, and the derivative of that was, what was that, remember? Yeah, negative sine x. And then we tried to use the fact that tan x was sine x over x, and the quotient rule. We tried to use, low d high minus high d low all over low squared, using sine and cosine as high and low respectively to come up with the derivative of tangent. So what did we end up with on that? Secant squared x. Okay? And then we sort of just conjectured that maybe the derivative of cotan would be negative cosecant squared, just because, look, it's the reciprocal of tan, right? So maybe we'll get like a reciprocal answer. And that's really bad logic, by the way. But it's just thought. Maybe it's cosecant squared. Maybe there's a negative, kind of like when we did from sine to cosine. There's a negative there, right? Maybe that happens again here. So I think it'd be worth our time to just do cotangent real quick. Maybe we could do secant together, and you could try cosecant on your own time. Okay? So we're going to try doing cotangent x. That's just cosine over sine. So the question is, what about the derivative of cotangent x? Okay, so the function is cosine x over sine x in disguise, right? That's what cotangent means, one way to write it. So your top function is cosine, your bottom function is sine, and if you run low d high minus high d low all over low squared on that, you'll be basically doing v u prime minus u v prime all over v squared. So let's just try it out here real quick. Maybe you can fill in the blanks. I'll give you a couple seconds. See what you come up with. Okay, so you should have ended up with, for v, you just copy and paste in here. So you have sine x. What did u prime turn out to be? Negative sine x. And u, of course, is just cosine x. It's given. What is v prime? Cosine x. And v goes on the bottom as well. Except I just wrote u. I meant the other guy. There we go. All right. So, on the top we have negative sine squared x and a negative cosine squared x all over sine squared x. And if you factor out the negative, you can see that this is really just the Pythagorean identity, sine squared plus cosine squared. Okay, so the top is negative 1, the bottom is sine squared x. We can interpret this to mean negative cosecant squared x. Final answer, let's go back and put that into our known facts table. We memorize this stuff, okay? Nobody in the right mind rederives it every test. You don't have time on the test to rederive. Memorize these facts. You'll be glad you did. Okay. Yes. Let's go back to the slide where we derived that. There it was. We're going to do the same thing with secant. Okay? I'll let you do cosecant on your own time. You're welcome. Let's go to the next one. What about secant x? What's the derivative of that? Well, if you can rewrite a trig function in terms of sines and cosines, you can find the derivative. So since it just means 1 over cosine x, we'll just use for our u, uno. Hey, that's cool. Uno starts with u. Okay. And for v, we'll use that cosine x. Okay. All right, so it's low d high minus high d low all over low squared. Make it fill in the blank. plug in the objects. Low, that's the bottom function. D high, what's the derivative of 1? 0. Minus high, that's 1. D low, what's the derivative of cosine? Negative sine x, some of you aren't too confident with that one yet. And cos x on the bottom. Okay, we get, this term just vanishes, doesn't matter. So we just have sine x on top and cosine squared x on the bottom. Okay, so how do we write that? Well, the sine over cosine portion can be thought of as tangent, right? And then there's another cosine on the bottom, so we can treat that as secant. So I'll show my work there. What I was doing was I was treating this as 1 over sine x, what am I doing? 1 over cos x. Take 2. 1 over cos x times sine x over cos x. So that's secant and tangent, respectively. Okay, so sometimes people ask me, Mr. Shore, what do you do when you go to the beach? Why do you go to the beach? And I'll say, derivative of secant. I seek a tan. Then I can be a tangent.
Oh, God.
Oh, boy. Math puns never get old. Who knows? Maybe that joke will help you remember that the derivative of secant is go to the beach. Okay? So do you think you could probably guess what the derivative of cosecant might be? Because I'm not going to do it. I'm going to have you try it on your own time. What do you think the derivative of cosecant would be? Just use this table so far and use your common sense. Anyone care to guess? Negative cosecant? Cotan x? That's actually the right answer. It's easy enough to verify. Just try 1 over sine x and do the quotient rule again. Okay. So I will write the answer, but you should really verify yourself. I want to save one of them for you to try. Think of it as 1 over sine and run through the same thing we did with secant. But it comes out to cosecant x, cotan x. This is what my wife does when she goes to the beach. I seek a tan and she cosec a cotan. Okay? Negative. All right. Any questions on that? Most people just memorize these. Think you might get them mixed up? Careful. They look kind of similar, you know. Okay, so there's a lot of questions on my mind. Like, I wonder how you would find, like, the derivative of, like, sine 3x, you know, that kind of thing. That's tomorrow. Sine 3x is an ugly, ugly ordeal. If you remember, it's sine of x plus x plus x, and you have to use an angle sum identity to split that thing 3 ways. Yuck. So we'll talk about that. That is going to introduce the chain rule for us. And that'll be cool. All right. But for now, we have 6 of them to memorize. I hope you're willing to do so. So let's talk about motion, because there are some objects in nature that move in a periodic or cyclic way, right? For example, anything that goes around in circles. Its equations of motion are not going to be like number 37. The equation of motion for an object moving in a round circular motion is going to have a cosine and a sine in it. Okay? If an object is repeating its motion at all, it's going to have in its equation of motion a cosine or sine in it. So can someone come up with some examples of natural phenomena that repeat themselves, or moving objects that repeat their path? Helicopter. What about a helicopter? The propeller, right? The propeller follows a cyclical pattern. Yeah. So the equation of motion for that helicopter rotor would include at least a sine and a cosine. Okay? Anything else? Just natural phenomena that either repeats itself or moving objects that repeat their path. A pendulum swinging back and forth, right? Waves on the ocean, right? They're not exactly predictable, but you can model them with sines and cosines and such. Yeah? Tornado? something spinning around in a tornado, its equations of motion would involve sines and cosines. Right? The rise and fall of our tides, right? We have high tide, low tide, you know? That's like cosine stuff, you know what I mean? So it is very possible that you'll crack open your AP Physics book tonight, and if you flip anywhere toward the middle, you might hit UCM, which is uniform circular motion, or SHM, simple harmonic motion, or one of those topics, or even waves like sound waves, light waves, lots of sines and cosines and those things. And we should know how to take the derivative of them if we're going to be taking the derivative of position functions to get velocities and such. Okay. All right, so I'm just going to pick a couple simple examples. I want to remind you from the last video that S is often the position function, and the derivative of S with respect to time is the velocity function. And if you take the derivative of velocity, okay, and then the derivative of velocity is also called what? What do we call the derivative of velocity? That's acceleration, right? Okay, so acceleration. This holds true regardless of the type of function you're using. Okay? So in this example, first example, you would just put an object's position is S of t equals, and I'm just using an example from the book, or one kind of like it. It's a little bit different. I could give you this position at time t, and we'll just use standard, just like meters and seconds and that sort of thing. So positions will be measured in meters, same with distances and displacements, and then time will be seconds units. Okay? I don't want to focus too heavily on units right now. We'll deal with that another time. Okay, so what would be something I might want to do with this? Maybe write down the what? Yeah, the velocity and acceleration equations, right? That might be important to me. Okay, so let's go ahead and try it. So how would you find the velocity? Well, you would actually take the derivative of the position. Remember, this first equation, the only thing it can tell you is where the object is when you give it a time. That's its only job. Not that helpful. But the velocity can tell you how fast it's going and which way it's going. That's important. Okay, so let's try to find the derivative. What was the derivative of cosine again? Negative sine. And for some reason, this always throws people off. If you're going to take the derivative of 2 sine t, okay, just ignore the 2 for a moment. Just ignore the 2. Ask, what's the derivative of sine? What is it? We said the derivative of sine is cosine. It's just straight up cosine. Okay, write that down. As for the 2 that was there, that just goes along for the ride. It is 2 cos t. Okay, so please don't try to use like the fancy product rule, you know, where u is 2 and v is sine t. Like that gets really confusing. Derivative of 2 sine t is 2 cos t. Okay, the derivative of a constant times a function is that constant times the derivative of that function. Okay, a lot of people messed it up last year. They didn't know what to do with that too. All right, there is your velocity function. What's its job? To give speeds and direction anytime you give it. All right, let's write down the acceleration function. So what is the derivative of sine? Remember, you can ignore the negative 1 there. Just forget it. Just leave it there, I guess. Okay, so what's the derivative of sine? Cosine. Okay. And what's the derivative of 2 cosine?
Negative 2 sine.
Yeah, it's 2 times the derivative of cosine. So basically it's negative 2 sine t. These are the easiest derivatives you'll do all year long. Sine becomes cosine, cosine becomes negative sine. It's that simple. Okay. If you want to put in units, this will be measured in meters, meters per second, and meters per second squared. So this makes me want to ask a slightly interesting question. Like, what would be the derivative of acceleration? Because I know the velocity is the derivative of the position, And the acceleration is the derivative of the velocity. So what comes after that, you know? And that's called jerk. Jerk. It's the derivative of the acceleration. Okay, so I'm going to write down the jerk function also.
What would that like represent? Like,
Yeah, it's very hard to understand what this means. If we know where an object is and how fast it's going, and which way it's going, and how fast the speed is changing, then what do we need jerk for? It's a good question. I mean, you don't really need jerk. You can chart out the whole future and past of the moving object using the first three. You know exactly where it is, how fast it's going, whether speed's increasing or not. You can even find force equals ma, you know, if you have the acceleration. You can find momentum using mv. You see what I'm saying? There's not much to be had from jerk. But some people are thinking that jerk, basically when accelerations change really rapidly, that might cause inner balance problems and like vertigo and that sort of thing might be related to jerk or something. So I don't know, it's just some people are conjecturing about jerk, but it's very hard to explain what this means. I mean, the units alone are funky. Meters per second cubed? What does that even mean? Okay, so it's how fast the accelerations are changing. But our book does mention it, and it's not hard to do. What's the derivative of negative cosine? Yeah, positive sine. Right. And then what's the derivative of sine? Just cos t, right? So just change your sine to cos, and if you see a cos, you change it to negative sine. Units on that, kind of hard to understand, meters per second cubed. But one of the questions might be simply, what are the velocity, acceleration, and jerk functions? So we just answered some of your homework style questions right there. Now they might give you a time. Okay, and only a mathematician would do this, I guess. But many of your questions ask things like, what are the position, velocity, speed, acceleration, and jerk at t equals, and you'd think they'd say t equals 1 second or t equals 5 seconds. They go random on us. T equals pi over 4 seconds. T equals pi over 4 seconds. I highly doubt you will see that in your physics class, because who measures time that way? Oh, I think you need to wait a second, right? You don't say, I think you need to wait pi over 4 seconds. Nobody talks like that, right? But what happens, it makes our answers real clean, real nice. Okay, question, and then we'll answer this question.
Is it intentional that if you took the derivative of j of t, you would go back to...
That is not a coincidence. His question is, what happens if you take the derivative of jerk? You actually end up back at the position function. This isn't true for all functions. Obviously, that wouldn't have worked on 37 over there.
Yeah.
But on this kind of thing, just so you know, tonight you're going to be asked to find the 999th derivative of cosine. So you need to think about this. Cosine becomes negative sine when you take the first derivative, and then negative sine becomes negative cosine on the next derivative, and then negative cosine's derivative is positive sine, and the derivative of that is cosine. So it seems like every 4 derivatives you recycle back to the original function. So what would happen if you took 999 derivatives of cosine? Don't shout it out. If you think you know, try it tonight. It's one of your problems. Okay, let's just try this real quick. Listen, all this is asking for is this, guys. I'm running out of time. They're asking for s of pi over 4. They're asking for v of pi over 4. When they said speed, they want the absolute value of your previous answer. Okay? And they asked for acceleration at pi over 4. And they asked for jerk at pi over 4. That's all you're doing. You've already got the functions. Plug in pi over 4. Okay, so let's run through this. Okay, so it's cosine plus 2 sine. See? Velocity was negative sine plus 2 sine. Speed is just the absolute value of that. Acceleration function was negative cos t minus 2 sine t. And jerk was sine t minus 2 cos t. All the sine t's and cos t's are rad 2 over 2 because we're doing pi over 4. So pi over 4 cosines vector 2 sines vector over 2. Pretty simple. You can simplify all those to get your answers. And don't forget the units. Alright, so we'll just go back and simplify these. So we have basically 1 root 2 over 2 plus 2 root 2 over 2. So this is 3 root 2 over 2. And this next one we could think of as 2 rad 2 over 2, right, minus 1 rad 2 over 2. So this just becomes 1 root 2 over 2. The velocity is measured in meters per second. So position we said we would measure in meters. So the position is 3 root 2 over 2, but the velocity is root 2 over 2. Okay, and then the speed on this particular problem happens to be the same as the velocity. So that's, of course, a coincidence. They can differ by a sign, right? One could be negative and the other positive. It's possible for velocity to be negative and the speed would still be positive. But here we see they're the same already. Okay, going on to acceleration. Combining these two fractions, we get negative 3 root 2 over 2. This should be measured in meters per second squared. And jerk gives us negative root 2 over 2, which is measured in meters per second cubed. And that concludes some of the essentials of 3.5. There is another topic in 3.5 about tangent lines, but I just want to remind you that the equation of a tangent line is always y equals f prime at a times x minus a, x minus a plus f of a, regardless of the type of function we're dealing with, as long as it's differentiable at that point, a comma f of a. Okay, so this is the tangent line. And the normal line, as you know, is y equals the opposite reciprocal of f prime of a times x minus a plus f of a. So you will see some problems where they actually ask you to draw a tangent line or get the equation of a tangent line or normal line. But it's just an application of this. And we do get some strange y-intercepts sometimes. And that just happens because when you're plugging values into these functions, you get some weird looking results. But there it is.